humans and ants are different. I really hope that I'm not the first one to tell you that. As a PhD student in mathematics, I offer you one distinction. While an ant walking on a sweet glazed donut can never tell whether or not the donut has a hole in the middle, I sure can. I study geometry of things. If you pick a point on any two-dimensional object that I study, if you zoom in close enough, an ant walking on it will see a nice turn in every single direction. Such an object is called by mathematicians a surface. Surfaces are all around us. Your phone screen, a donut, a pretzel. In fact, we are all standing on the Earth's crust, which is a surface too. Well, one question mathematicians like to ask is, how can we tell two surfaces apart? It's not very hard to tell that's a donut, that's a pretzel. Well, let's not get ahead of ourselves. Let's just remind ourselves that it took us so long to universally accept that the Earth is not flat like a disk, but rather the Earth's crust forms spherical-like planet. It's not even a problem of perspective either, because if someone hands you these three complicated-looking surfaces that may fit in your hand just fine, you might have a headache trying to figure out, oh gosh, are they the same or are they different? So what we need to answer this question then is a framework. This is where mathematicians come in. Oftentimes, ideas in mathematics take off from a very concrete example, like this one. And then mathematicians try to get rid of the redundancies and reformulate the question in abstraction so that the result applies in greater generality. Oftentimes, more than I hope, this beautiful process gets dismissed or overlooked. It's a pity, and so it's my hope today to tell you in these 8 minutes some of these beautiful ideas. Before I dive further in though, let me tell you what has come out of all this. This iPhone of mine recognizes my face as the password. How could it even detect my face of all the faces that it sees? This would have been impossible without the mathematical theory and framework that mathematicians have developed for the past 100 years. Now, I actually want to tell you what I mean when I consider two surfaces the same. By this, I mean that you can deform, stretch, distort, shrink one surface to the next without tearing it or breaking it apart. For example, if you have a ping pong ball, you try to shrink along the equator, you'll get something like an hourglass. This concerns the topology of the surface, and we say that the ping pong ball and the hourglass have the same topology. A very classical example of this is that topologists, people who study topology, cannot tell a donut and a coffee mug apart. This is why. So in 1895, Henri Poincaré came up with an idea, a very revolutionary idea, to answer the question that has now been rephrased. When do two surfaces have the same topology? He discovered that the way that you tie a rubber band around the surface actually encodes so much information about the surface itself in an object which is algebraic called the fundamental group. For example, take a tennis ball or ping pong ball, if you will. Try to wrap a rubber band around it. No matter how hard you try, you can always slide it off. Look at this guy. Right? So it's always possible to slide it off. On the other hand, this configuration of a rubber band and a coffee mug cannot be undone unless you cut the rubber band or you break the mug itself. This shows that a tennis ball and the coffee mug have different fundamental groups, hence different topologies. Turns out, you can tell the topologies apart by essentially counting the number of holes, which mathematicians call genus. And more is even true. We can list them all by the genera, which is the plural form of genus. That's the surface of genus 0 with 0 hole, surface of genus 1 with 1 hole, 2 holes, 3 holes, and so on. Oh, good. Seems like we have answered our question. It's rather unsatisfying, isn't it? Because to topologists, all faces look the same. They have the same topology, right? So this is rather unsatisfying. Now, the perspective of an ant will prove useful. Imagine an ant walking on a surface. It has just located its food source, okay, with the local knowledge of the local topography and a strong sense of smell. It will try to get there using the shortest possible path, which means that we can use an ant to tell us the distance between any 2 points on the surface, or any loop on the surface if it walks around on a circle. And you can probably imagine that if you know the distances between any 2 points at all, you should be able to recreate what the surface globally looks like. For example, these 4 surfaces have 2 holes. They're all surfaces of genus 2, but to get from one point to another, that requires different distances. And this concerns the geometry of the surface. And as this proves, one single topological surface can have a lot of geometries. And in fact, the miraculousness of this is that if you know the length of simply 9 loops, you can tell the ant which surface is actually walking on. And in the same way, the distances between the eyes, the nose, and the mouth can help us identify the geometry of our topological face in the facial recognition algorithm. The application doesn't stop there. The theory of surfaces has proved useful in making the diagnosis of the brain better. It helps us understand the shape of the brain, and this is in the field of brain morphometry. While surfaces seem to live in their own abstract world, the applications behind them and the mathematics behind them have enabled the world's technological progress. And with this application and beauty, the world of mathematics, with its open arms, invites a curiosity within you to come in and explore. Thank you.